So on pages 165 and 166, we're going to review logarithms. And a logarithmic function is the inverse of an exponential function. So logs and exponentials undo each other. And really the key to this section and being successful on this test is knowing the following statement. If you're given something in exponential form and it's not helping you, then you need to convert it to logarithmic form. And if you're giving something in logarithmic form and it's not helping you, then you need to convert it to exponential. And to convert it, this is what we do. Both exponentials and logs have a base. In this case, 2 is the base, and in this case right here, 2 is the base. The easiest way for me to remember how to convert these is that you always start at the base, right here, the 2, and you're going to make a little swooshy, or a swoosh, and you're going to circle around the equal sign. So the first thing we touched was 2, and then we went by the 8, and finally we stopped at the 3. This is an exponential form, so to go over here to log form, the first number again you touched was 2, so you have log base 2. The next number you touched or went by was the 8 equals 3, which is exactly what is written right there. Same idea. Let's say that I was given this and I need to convert it. I'm going to start at the base, which is 4, and I'm going to make my little swoosh around the equal sign like that. So 4 to the 0th power, 4 to the 0th power has to equal 1, which is exactly what's written right there across the page. I mean, we know it's a true statement because anything to the 0th power is 1. So let's try the following. 3 to the 4th is 81. So first you touch your 3, so you have log base 3. Next is 81 equals 4. Here we start at the 7 and we go around the equal sign. So 7 to the first power equals 7. Around the equal sign. 14 to the 0th power equals 1. Around the equal sign. Log base 1/2 of 32 equals -5. So hopefully now you can convert. So if I go down here to evaluating log functions, it says to help you find the value of log base b of y, ask yourself what power of b gives you y. For example, so if we're doing this one right here, 4 to some magical power equals 64. 4 to what power is 64? Well, 4 to the 3rd. So if we want to do these following problems without a calculator, so 5 to some magical power equals 0.2, and I'm going to rewrite the 0.2 so that you can see the answer. 5 to some magical power equals 1 over 5, because 2/10 is the same thing as 1 over 5. Well, this 5 right now is on top of the fraction. There's like an imaginary fraction right there. And to send the 5 down to the denominator, I need to have the exponent be negative. So I know I have to have a negative. And 5 to what power is 5? Well, it's just 5 to the 1st. So for this one, 1/5 to some magical power equals 125. The first thing you should notice that the answer is going to be negative because I need to bring the 5 up to the top of the fraction. So now with the negative sign, you brought 5 to the top of the fraction. And so now 5 to what power is 125? Well, 5 to the 3rd. So -3 is my answer. And then this last one, 36 to some magical power equals 6. To get from 36 to 6, I know that you want to tell me divide by 2, but we can't divide by 2. We can only use powers. So if I were to square root it or put it to the 1/2 power, you'd get 6. So the answer here is 1/2. Okay, so on page 166, there's some more notes. It says the common logarithm is a logarithm with base 10. We're going to use that a lot. And it's denoted by log 10 or just log. So if you see just log and there's no base written, it's implied the base is 10. The natural logarithm is a logarithm with base e, and we talked about e a couple days ago in our notes. And e is just, let me write it in pen. E is kind of like pi. It's about 2.71 ... forever. And it's denoted by log base e, but more frequently you're going to see it written right here, right there, as ln. So if you see ln, you need to know the base is e. Your calculator has a log button. It also has an ln button, and I will show you right where those are. They're both in blue, so you have to press the control first, but the ln's right there and the log's right there. And it says most calculators have keys for evaluating common logs and natural logs using your calculator to evaluate the following. So I'm just going to turn my calculator on, and if I can get it to show up for you. Grab the light really quick and make it better. If I do the first one, I'm going to press control and then the log, and then it's going to ask you what base you want. The base here is implied as 10, so you can type 10, but if you just leave it blank, the calculator assumes you mean 10. And then you need to press control. Let's do that one more time. So I have my log entered. You have to press control and the enter button so that it approximates it for you. And so we're going to use 3 decimal places, 0.903, and then ln of 0.3, and then control enter, negative 1.204. And then if I do the next one, I'm going to type log of 0.85, control enter, negative 0.071. And the last one, ln of 22, 3.091. Okay, so the other thing you need to remember is some key facts about inverse functions. When we did inverse functions and we talked about f of x and g of x, and we had these two functions, they were inverses if and only if f of g of x equaled x and g of f of x equaled x. So when you plugged g into f, you had to get x, and when you plugged f into g, you had to get x. Well, the same thing is true about logarithms and exponentials. If they are inverses, they have to equal x. So here, we plugged in the exponential into the log function, and we got x right there. So that means they're inverses. We got to do it the other way. We plugged in the log function into the exponential, and we got x. So that means that they are inverses. So down here, I'm going to rewrite this problem. This says b raised to log base b of x is x because they're inverses. The key here is that the two bases are both b. So, and then you have this x left over, which ends up being your answer. So if I rewrite the one below it, I have 10 log base 10 of 4. Because the exponential has a base of 10 and the logarithm has a base of 10, that's the key. The bases are the same. Those two things into each other, and you're left with 4. Same thing over here. I have a logarithm of base b and an exponential of base b. Because the bases are the same, this power up here ends up being my answer. So I have log base 5 of 25 raised to the x. Well, those bases aren't the same, but we can rewrite 25 so that its base is 5, and we rewrite that as saying 5 squared. Then you can multiply those two powers together and get 2x. So now I have log base 5 of 5 raised to the 2x. These bases are the same, so my answer is simply just 2x. And then the last little set of rules. Log base a of 1 equals 0, because if you convert this a to the 0th power, anything to the 0th power is always 1. Log base a of a equals 1 because a to the first is 1. And these two logarithms are equal if and only if x and y are equal because the bases were the same. Go back to Edmodo, and on page 167 we're going to talk about graphing logarithms by hand, which you're going to have to know because it's going to be on your test.